little bit of candlelight, that'll see you through. Maybe a little bit more intense than candlelight. Heat up a piece of magnesium. There we go. Mg plus O2, MgO is being produced, and that's quite a good amount of light. Can't look directly at that, of course. You can on DVD. I can't when I'm looking at it. But, interestingly, look at that. There's no more magnesium there. That's a compound, magnesium oxide. Okay, so magnesium and oxygen, they come together and make magnesium oxide. But why did those elements want to do that in the first place? Well, elements like to be able to bond together to lower the total amount of energy they have as individuals. When they come together, they release energy and form a new system that is actually more stable than the two of them were apart. That's the whole idea behind the whole universe. It's stability gained through this type of chemical bonding. Now, electrons are actually shared in chemical bonds, or they're actually transferred or exchanged. And let's talk about the ones now where electrons are transferred. Generally, it's between a metal and a non-metal, or a cation and an anion. So, Na positive here is the cation, and F negative the anion. Now, why do they have those particular charges? You can look it up on the periodic table. It has to do with their tendency to be able to gain or lose an electron or electrons. It might be more convenient for them to lose 2 or 3 electrons to become more stable. In the case of sodium, it likes to be able to lose 1 electron, if you can use that word like. Sometimes we personify in chemistry or anthropomorphize things and kind of reduce it down to the human level. But of course elements don't want, they don't desire, they don't like anything. But what sodium has a tendency to do is to lose 1 electron when given enough, just a little bit of energy in order to do so. Now, fluorine on the other hand, that likes to acquire, acquire an electron to be able to become more stable. And so if Na is a positive and F is a negative charge, and you can look those up on a periodic table, then when these two actually do that type of exchange, an electrostatic interaction keeps them together because one is positive and one is negative, and dislike charges will attract one another. So, how many NAs does it take to bond with F in order to get a stable compound? I lose 1 electron, I gain 1 electron, and so the formula is NaF. That's the formula for the compound sodium. And then we take fluorine, and then we say, okay, drop the INE and add IDE, sodium fluoride. Okay, now, you take a look at magnesium, which actually can lose 2 electrons. That's on a periodic table, check it out. Chlorine wants to gain only 1. So what's the story there? Magnesium is saying, hey, I'm going to lose 2 electrons. This is, but I only require 1. So if that's the case, then you need another chlorine to come by, another Cl negative, and both of these can each gain 1 for a total of 2. So this is where we get the formula for magnesium chloride. 1 magnesium for every 2 chlorines, and the name of that compound, magnesium chloride. Now, you can say, well, you know what? I just learned that you can just take that 2 and put it there, and take that 1, which is there, and put it there, and then you get the formula. Well, yeah, okay, that's a kind of a convenient way to do it, but I hope you understand. You got to understand. And you have to understand that this is the principle that we're going by here. There's no real exchange of charges. There's just that we need 2 of these for every 1 of these. And I hope that you get that. Now, look at this one, for instance. You got tin with a 2 positive and O with a 2 negative. See, and a lot of chemistry students who are actually quite bad would say, oh, just put the 2 there and put the 2 there and there we got it. No, you can't do that. You can't do that. You have to understand that this is saying, I want to lose 2 electrons, and I want to gain 2 electrons. So the ratio of reaction between those two is just 1 Sn for every 1 O, and so that is how you write that. Now some of you are going to say, well, yeah, just reduce these to the lowest whole number ratio and then switch them. Yeah, okay, but do you understand the principle? That compound is actually called tin 2 oxide. And the reason we have to say the 2 is because tin is a multivalence, and valence just means charge, okay? It's a multivalence type of element that's found on the periodic table, and generally you'll see that the metals in the metal block of the periodic table can have more than one type of charge. There's one that's more popular than another one, generally, that exists in nature, and that's indicated on the chart.